In this video, we will learn how to describe the history and development of the periodic table, name the key people involved, and outline their contribution. Many scientists have attempted to organize the known elements to make sense of their properties and relationships. In 1789, French scientist Antoine-Laurent de Lavoisier published the first modern list of elements. Lavoisier categorized 33 elements into gases, metals, nonmetals, and earths. In 1817, German physicist Johann Wolfgang Döbereiner grouped together elements with similar properties. He called these groupings, which often contained 3 elements, triads. In 1864, British chemist John Newlands organized the 62 known elements by increasing atomic weight. Newlands noticed that when the elements were listed in order of atomic weight, every 8th element had similar behavior. So he arranged the elements into rows and columns so that the elements were still in order of atomic weight, but elements with similar properties were grouped together. 5 years later, a new periodic table would be proposed that would create the framework for what would eventually become the modern version of the periodic table. In 1869, Russian chemist Dmitry Mendeleev published his first periodic table. Like Newlands, Mendeleev organized the elements into rows and columns. The elements increased in atomic weight down a column, and elements that had similar properties were grouped into the same row. When constructing this periodic table, Mendeleev noted that tellurium had similar properties as the elements oxygen, sulfur, and selenium. He also noted that iodine had similar properties as the elements bromine, chlorine, and fluorine. As a result, he concluded that tellurium and iodine should not be listed in order of increasing atomic weight, so that tellurium and iodine were in the same row as elements with similar properties. Tellurium proved to be a constant dilemma for Mendeleev, as the atomic weight changed several times while he was constructing his periodic tables. Mendeleev also noticed when ordering the elements that there appeared to be some elements missing. When there wasn't an element with properties that he expected, he left a gap for these yet undiscovered elements. Mendeleev's first periodic table wasn't perfect, and there was still some uncertainty, particularly as elements got heavier. In 1871, Mendeleev revised his periodic table. His revised table had 12 rows and 8 columns. He called each of the horizontal rows a period and each of the vertical columns a group. Modern periodic tables still use this distinction. The elements were still listed in order of increasing atomic weight, this time from left to right across a period. And elements that shared similar properties were organized into the same group. This revised periodic table still had gaps for elements that were yet to be discovered. Mendeleev listed the expected atomic weights of these elements and even predicted their properties based on the properties of elements near them in his periodic table. 3 of the most notable elements Mendeleev predicted were expected to have atomic weights of 44, 68, and 72. He called these elements eka-boron, eka-aluminum, and eka-silicon. Each of these elements were later discovered and were found to have atomic weights and properties similar to those Mendeleev predicted. In addition to leaving gaps for some undiscovered elements, Mendeleev also proposed new atomic weights for a few elements which didn't seem to fit his table. Beryllium's accepted atomic weight at the time was 14, the same as nitrogen. But beryllium had similar properties as the elements magnesium and calcium, so Mendeleev proposed an atomic weight of 9.4 in order for these elements to be grouped together. Similarly, uranium had an accepted atomic weight of 120, but Mendeleev proposed that uranium should have an atomic weight of 240 in order to be grouped with the element tungsten. Mendeleev's proposed atomic weights are close to the accepted values today. Beryllium has a relative atomic mass of 9, and uranium has a relative atomic mass of 238. Although several arrangements of the elements came before Mendeleev's periodic table, his table often receives the most credit and is frequently referred to as the first periodic table. But Mendeleev's table did have some flaws. Mendeleev did leave gaps in his periodic table for undiscovered elements, but he did not leave room for or predict the existence of the inert gas elements. In addition, the elements copper, silver, and gold shared some properties with the elements in Group 1 and some properties with the elements in Group 8. So Mendeleev listed each of these elements twice. Another potential issue had to do with the difference in atomic weights of successive elements. The atomic weights of boron and carbon differed by 1 unit, but the atomic weights of carbon and nitrogen differed by 2 units. This made some scientists question whether there were more undiscovered elements that belonged in between some of the elements on Mendeleev's periodic table. More flaws became apparent as further scientific discoveries were made. As more elements were discovered and atomic weights were more accurately measured, more instances occurred, like the issue with tellurium and iodine. For each of these pairs, the element with the higher atomic weight needed to be listed first in order for both elements to be in the same group as elements with similar properties. The existence of isotopes was yet another complication. Isotopes are atoms of the same element that have a different atomic mass. For example, some atoms of the element hydrogen have an atomic mass of 1, some have an atomic mass of 2, and others have an atomic mass of 3. If the periodic table is organized by atomic weight, then each isotope of an element might need to be listed separately. Major discoveries in the early 1900s would help to solve many of these issues. In 1911, following the results of the gold foil experiment, Ernest Rutherford proposed a new model of the atom. In this model, negatively charged electrons orbited a central nucleus. The nucleus was positively charged and contained most of the mass of the atom. Shortly after Ernest Rutherford's proposal, Dutch physicist Antonius van den Broek suggested that the charge of the nucleus was exactly equal to an element's atomic number. The atomic number was the position number of the element on the periodic table, where the first element listed had an atomic number of 1, the second element had an atomic number of 2, and so on. Van den Broek's theory would be proven true in 1913 by a young British physicist named Henry Moseley. Henry Moseley designed an experiment to observe how X-rays emitted by an element were diffracted. When the power supply was turned on, the elemental sample would emit X-rays, which were diffracted onto a photographic plate. Each element tested produced a unique pattern of lines on the photographic plate. Through some calculations, Moseley was able to directly relate the pattern of lines produced to an element's atomic number. Moseley performed his experiment with the elements aluminum through gold and found that the X-ray diffraction was directly related to atomic number for all of the known elements. Based on his findings, Moseley proposed that the elements should be organized by increasing atomic number, not by atomic weight. Here we've shown the elements listed in order of increasing atomic number in 3 rows, but in Moseley's original paper, these were listed in a single column. Organizing the elements by atomic number solved the flaws with Mendeleev's periodic table. This organization accounted for and included the inert gas elements, and no element was repeated more than once. Unlike with atomic weight, the difference between the atomic numbers of successive elements was always 1 unit. In addition, the pairs of elements that had to be reversed when listed by atomic weight were in the correct order when listed by atomic number. Finally, isotopes were no longer an issue if the elements were listed by atomic number. This is because while isotopes of an element have a different atomic weight, they have the same nuclear charge and therefore the same atomic number. In addition to solving the flaws with Mendeleev's periodic table, Moseley's discovery was important for 2 more reasons. Like Mendeleev, Moseley predicted the existence of 4 undiscovered elements. All 4 of these elements would later be discovered and named technetium, promethium, hafnium, and rhenium. In addition, Moseley's experiments provided a concrete way to determine if a substance was in fact a new element. Each element produced a unique pattern of lines on the photographic plate. So if the lines produced by a substance were different from the known elements, then a new element had been discovered. Henry Moseley's work paved the way for the modern periodic table, but even more discoveries about the nature of the atom would lead to the periodic table that we know today. In the same year that Moseley suggested organizing the elements by atomic number, Niels Bohr proposed a new model of the atom. Bohr suggested that electrons in the atom orbited the nucleus in discrete regions called energy levels. Bohr's model would be expanded upon over the years to include energy sublevels and orbitals. Then, in 1920, Ernest Rutherford published another discovery. He had discovered a new subatomic particle called the proton. Protons are found in the nucleus of an atom and have a positive charge. The number of protons in an atom of an element is equal to the nuclear charge, which is equal to the atomic number. The modern version of the periodic table is arranged based on all of these discoveries. The modern periodic table is organized into 18 columns and 7 rows. Just like with Mendeleev's periodic table, the vertical columns are called groups and the horizontal rows are called periods. Based on Henry Moseley's work, the elements are listed in order of increasing atomic number from left to right across a period. We could also say that the elements are listed in order of increasing number of protons from left to right across a period. The elements are also organized according to how the electrons fill various energy levels and sublevels. Elements found in the same group have similar properties. This is because the electrons in atoms of elements in the same group have a similar electron arrangement. In addition, atoms of elements found in the same period have the same number of electron shells or energy levels. Before we summarize all that we've learned about the history of the periodic table, let's take a look at a question. The symbols and information for 5 elements are shown below. How would these elements be ordered according to Moseley's periodic table? Henry Moseley was a British scientist who studied how X-rays emitted by an element were diffracted. In his experiments, a photographic plate was exposed to the X-rays. The X-rays produced lines on the plate. The bands produced were unique for each element. Through some calculations, Moseley discovered that the lines produced were directly related to the element's atomic number. Moseley then suggested that the elements on the periodic table should be ordered by increasing atomic number instead of by increasing atomic weight. So, to organize the 5 elements according to Moseley's periodic table, we must put them in order of increasing atomic number. The atomic number is written above the chemical symbol in each box. Looking at the answer choices, we can see that the answer choice that correctly lists the elements by increasing atomic number is answer choice A. Therefore, the correct order of the elements according to Moseley's periodic table is answer choice A. Now let's summarize what we've learned. There were many early attempts to organize the elements to make sense of their properties and relationships. Dmitri Mendeleev, a Russian scientist, is often credited with creating the first periodic table. He organized the elements by increasing atomic weight. He also grouped elements with similar properties into the same column. He called the columns groups and the rows periods, terms we still use with the modern periodic table. Mendeleev's periodic table was special because he left gaps for undiscovered elements and proposed new atomic weights for elements that didn't fit his table. Mendeleev's periodic table did have several flaws, including that it did not account for the inert gases or isotopes, and some pairs of elements needed to be written in reverse order so that they were grouped with elements that had similar properties. Henry Moseley was a British scientist that discovered a direct relationship between the X-ray diffraction pattern of an element and the element's atomic number. He suggested that the elements should be organized in order of increasing atomic number. Like Mendeleev, Moseley left gaps for elements that would later be discovered. The modern periodic table is organized by increasing atomic number which is the same as the number of protons in all atoms of an element, and by how electrons fill various energy levels and sublevels in an atom.